All right, so now we're going to do some, we're going to talk about another favorite topic of mine in, uh, in computer science. All right, the difference between compile time and one-time resources, right? If you're taking 2001, this is a big, well, if you're taking any computer science, this is a big topic. What's available to you? Compile time is what's available to you as you're designing the algorithm before you have the input. And runtime is what's available to you after the input is provided, right? So I would say the split between compile time and runtime is in fact uh, when the input arrives. All right, so let's think about this. Remember here, the prover comes up with the algorithm. The prover comes up with the algorithm at compile time. Well, before compile time, it's this line before. I'm just looking at my slides over here. There's a real delay between when it arrives and I arrive, right? Sorry about that. I talk here. I'm just watching it. There's a big delay. All right, sorry about that. The internet is being slow. All right, so I come up with this algorithm at compile time, and I have to do it without knowing the input, right? Nobody's given me the input yet, and I need to fix what the algorithm is. And what's key is that there's going to be a finite description, right? Code is a finite description. I describe with the finite screen my algorithm A, right? And then after the algorithm is fixed, right, then the adversary gets to choose the input. So we call that runtime, right? We're actually running the algorithm. We get an input. We already know, and the algorithm's been fixed. So because the algorithm was fixed, and then we came up with an input, the input might be much, much bigger than the algorithm, right? You can make remember that game in which you come up with a number, then I come up with a bigger number, right? You can say 1,000,000,000,000, I can say 1,000,000,001. So you can come up with an algorithm with as much code as you want. But once you fix it, I'm going to come up with an input that's bigger and scarier, right? That's the whole game of computation, is that you say 1,000,000,000, I say 1,000,000,001, all right? So now there are resources that happened at runtime, right? What are the resources? After you choose the input, I could give you, you can have more time, you can have more memory, right? So they're runtime resources versus compile time resources. All right. So let's talk about that more, right? When I'm coming up with the algorithm, I take the algorithm and I type in the code, and then I print it on the printer, right? And the algorithm will have some number of lines of code, right? Might have 10 lines, it might have 1,000,000,000,000 lines of code, right? And so let's just have new notation. We're going to have the notation here. Lines AI will say what? It will say algorithm A, when running on input I, will have K lines of code, right? It's just something we can talk about. Now, I bet you all of you are thinking, why did we put I in there, right? Because we all know that the number of lines of code doesn't depend on the input, right? Why did I put I here? Well, the reason I put I there is because we want to be able to say that the number of lines of code doesn't depend on the input. And in order to be able to talk about the fact that it doesn't depend on the input, we have to have our notation allow the possibility that it does. All right, so this is allowing the possibility that the number of lines of code depends on the input. And we will then talk about how it doesn't depend on the input. All right. Now, in contrast, running time, right? Here's how much time does it take for algorithm A to solve input I. There's a certain amount of time, right? Seconds, computer cycles, whatever it is. And here's just the little picture I like to stick in sometime. That there is me. That's my father. And one of the things that he did was talk about running time, poly time versus exponential time. And so I stuck that in. 63, I about when he was doing his famous work was in 63. And the reason I put 63, that's when I was born. All right, so now let's have our longer logic statement. Here we're saying there exists an algorithm that for all inputs, it solves the problem, it uses so many lines of code, and it has a certain running time. All right? So, oh, but we have a K and we have a T here. At the moment, they're free variables, right? Because at the moment, they're not quantified, and I want to quantify them. So K, now is this sentence true for every K? No, no. Our algorithm is going to have some number of lines of code, right? There exists a K. So that's what is, we're going to be saying there is some K. I just stretched my legs out a bit. All right, so what about time? Does the algorithm on an input have every type of time? No, there's one time. There's some time that it has. There exists a time, right? All right, so here we have an exists K and an exists I, exists T, but where are we going to put them, right? And so let's who gets to choose the K, right? When does it get chosen? Does it get chosen? Does K get chosen at runtime before the input, or after the input, or at compile time before the input? Well, clearly it gets chosen when you design the algorithm, right? So it gets chosen at compile time. It doesn't depend on the input. And when I say K is a constant, what do we mean by K is a constant? We mean that it's chosen at compile time. It can be anything you want, but it's chosen at compile time. All right, so there it is. We're choosing it at compile time before the input, right? All right, what about the running time? When is the running time chosen? It's chosen, running time is chosen at runtime. Surprise, surprise, right? Runtime. All right. So I was just remembering that somebody had a problem with my word compile time and runtime, and I wonder if I fixed that. I don't remember. Anyway, it depends on the input. So, oh, yeah. So compile time doesn't mean how much time it takes to compile. It means the stage in which we're compiling. That was what some student I was doing these slides, and he thought I meant compile time, meaning how long it takes to compile. We're not doing that. All right. I didn't fix those slides. I don't know what I'd call it instead. Run period, run stage, run. Oh no, compile period, run period. Anyway, this is the period of time where we're compiling, and this is the period of time in which we're running, right? All right. So, so yeah, we choose the amount of time it takes to run at runtime, and that is confusing. All right, so maybe people can brainstorm how we could switch those words. All right, so now the exists K, we've decided it's going to be before the input, right? But do we put it here or do we put it here, right? Do we choose the K, the number of lines of code, before we come up with the algorithm or after we come up with the algorithm? Well, the truth is exist A, exist B is the same as exist B, exist A. It doesn't matter which order you put them in. So here's our sentence. We're going to say there exists an algorithm, there exists a K, so that for all input, there exists some running time such that you've solved the problem on that input. The number of lines is K, and the running time is T. All right. So let's bring our good woman over here back again and see what she has to say, right? She says, we work this out at, we do the inner thing and we see what each line means. So here, we have a lot of free variables here, right? A's algorithm's free, the input's free, the problem's free, the K's free, right? The T's free. We got a lot of free variables. So what does it say? It says on input I, algorithm A solves P with K lines of code in time T, right? Everybody see that that's what it says? Okay, great. So now we bring in some of our, right here we bring in for all input there exists a time, and so we have fewer free variables. So we want to talk less about the input and less about the time. So we simply say algorithm A solves problem P with K lines of code, right? Here I'm talking about the free variables. Algorithm A solves problem P with K lines of code. You know, I didn't mention the input. I didn't mention the time. Now, here I'm going to put a little extra thing. I'm going to actually say, and the time will depend on the input, right? All right. So now we bring in these things, right? Now, when we bring in these things, we no longer, the only free variable is P. So what does this thing say about P? It says problem P is computable. This whole thing there, all it says, problem P is computable, right? We're implying that there exists an algorithm. We're implying that that algorithm will have some number of lines of code. We're implying that it's going to work for every input, and that for every input, there will be some running time, right? But we can slip in these extra statements. It's computable, and there's some number of lines of code that doesn't depend on the input, and there's some running time that does depend on the input, right? Does that make sense? All right. Are we doing okay here? All right. So now, so this, what am I typing here? I copied it from 2001 last term. I had an exam question, and these are the words I typed for their exam question for 2001. And of course, they didn't do very well. And that's why I started teaching this course. All right. I want you to deeply understand this. Do you deeply understand it? Can you explain to me the game used to prove that this is true? Can you specify who in the game provides what, in which order they provide it, and why they provide it, right? Can you explain which values depend on which values, right? Can you explain how the dynamics of this game are affected by the order in which people go and who decides what? Can you tell me what this sentence means, right? Tell me something deep about what this sentence means, right? That's what I asked on the 2001 exam. All right. So I'm getting distracted by people's comments, so I'm going to just see if I turn those comments off. All right, good. If you actually want to say something, holler out. All right. I assume that the chat is for you to talk amongst yourselves. I don't know how rest in peace. All right. Actually, rest in peace. I'm of the age just that my friends' parents are all dying. I've had 4 friends' parents die in the last couple of weeks. Actually, and one friend's son died the last week. It's been a bad day for. Okay, let's see. What are we doing here? There exists an algorithm. There exists a K, right? So this is the answer I gave for the 2001 exam. I said, well, exists a K, exists an A. The prover is invested in proving that the sentence is true, right? The prover, actually, maybe this wasn't a 2000, maybe this was 2001 assignment for this term even. I don't remember. Somewhere it's 2001. All right, so the prover is invested that this is true. The prover gets to decide the exists. The prover starts by designing all aspects of the algorithm, its code and its variables. The prover, it's important that the prover does this before knowing the input. When he designs the algorithm, he gets to fix the number of lines of code, and we'll denote that with K. The prover, why does the prover get to decide the K? Because not all values of K will work, and he's invested in proving the sentence is true. So he will choose the K to be a K that works, right? Now K and A are fixed. What does the input do? What does the adversary do? The adversary is invested in the sentence being false, right? So the adversary gets to come up during runtime, right? He gets to come up with an input. Oh, he wants to give the guy as hard of a time as possible. So he produces the worst case input. He comes up with an input that he knows the algorithm, and he comes up with an input that is hard for that algorithm, right? Some algorithms might work for some inputs, and other algorithms work for other inputs. So he knows the algorithm, and he comes up with an input that doesn't work for that algorithm, right? All right, so now once we have the input, then the prover again gets to decide, right? The prover came up with the algorithm, so the prover gets to come up with the runtime. The runtime depends on the algorithm, right? But it also depends on the input. All right, so then when is it all true? It's true when the prover solves the problem and has the right number of, the algorithm has the right number of lines of code. And here, remember we said that the K doesn't depend on the input. I'm claiming that this here assures me that K doesn't depend on the input. Why not? Well, in the game, the adversary wants this to be false. And if I fix if this K here depended on this input, then the adversary would have given me a different I so that this would have been wrong, right? We fixed the K here. The adversary knew the K when it came up with the input. And if there was some input where it was a different K, then the adversary would have given us that different input, and the adversary would have won right off the game, right? And the adversary wants to win. But because the adversary is not winning, that means that the K doesn't depend on the input. All right, people following this?
Sorry, could you repeat that again?
All right. I want to say, everybody knows that the number of lines of code in your algorithm doesn't depend on the input, right? You printed the code out. Now it's on paper, right? So the number of lines of code is not going to change. And how is that represented here, right? It's represented by the prover who wants to make it true. Prover wants to choose a K so that this is true, right? The prover already chosen the algorithm. So the prover wants to choose a K to make this true, right? The prover fixes the algorithm and then fixes a K so that this is true. And what K does he fix it to? He fixes it to the number of lines of code in the algorithm, right? But let's for a minute pretend that the number of lines of code in the algorithm depends on the input. That means on some inputs we get one K, and on some inputs we get a different K, right? Now, which K would the prover come up with? If it's some inputs you get one K and some inputs you have that other K, he's gonna have a hard time choosing that input, right? It's choosing that K. But he has to fix some K, right? So he fixes some K. And then the adversary gets to choose the input. And he will win if any of these things are wrong, right? He wins if the algorithm doesn't solve the problem, right? He also wins if the algorithm on that input has a different K, right? So if there was an input on which the K would be different, then he would give me that input, right? But we're assuming that he loses this game. We're assuming that this statement is true. So what is this statement saying? This is saying if it's true, then the adversary is guaranteed to lose the game. And if the adversary is guaranteed to lose the game, then there's no input the algorithm can give to make the number of lines of code different, right? And what does that tell me? That tells me that the input doesn't depend on K. Oh, no, sorry. That tells me that the K doesn't depend on the input, right? Does that make sense? I think there's so much deep meaning in here, right? If you can understand the nuances of what this is saying, right, it's going to really help you in computer science, right? You have to know what depends on what in these games, right? People follow this?
I have a question actually.
Yes, I like
Oh.
questions.
So when you say that there exists a runtime T, then
Yeah.
what represents the compile time?
Oh, see, that's why I don't like the word compile time. All right. I said this in a minute. Everybody, let's brainstorm how we can fix the word compile time. The word runtime in computer science theory, as far as I know, we should Google it and see what Wikipedia says about runtime. Because
Doesn't time step work as well?
well, that's one time step. I have two meanings for the word runtime. All right. The one meaning for the word runtime is how much time does it take for the algorithm to run on a given input, right?
That's how I understood it.
That's running time, right? But people also say compile time and runtime, and that runtime means something different. That means the period. What that means is that there's a game happening, and in this game, there's a split in the game. There's a period where before the input, and there's a period after the input. And the period of time before the input is called runtime, and the period after is called before is called compile time, and the period after is called runtime. Like, have you ever heard the expression runtime error versus compile time error?
Yeah, we did. Because in Java we have syntax, we have runtime, and we have logic error. These are the three types.
Right,
yeah.
right.
We
exactly.
know that runtime is basically runtime error is basically
Syntax
so it
error.
falls under
So that's where I'm coming from when I say compile time and runtime. I'm talking about compile time error, runtime error. Like when you give your Java code to a compiler, it doesn't know what your input is, right? And it's not running your code. So a bug that depends on running it on a particular input, it's not going to find that bug, right? But if there's some syntax error, or there are various errors that the compiler can find, and they find them just looking at your algorithm during compile time. And so here I'm talking about, that's what I'm talking about, runtime and compile time.
Yeah,
Right?
so compile time is syntax and runtime is runtime error. That's the
But so compile time is actually not like represented within this logic sentence, right?
No. In fact, I would say, well, it is. I would draw a big red line here, and this period of time here where these things are being constructed is compile time. And this time here where we already have the input is called the runtime period of the game, right? And this slide is particularly confusing because this T has to do with the running time of the program, while this period has to do with the period in which we're coming up with the input. And I'm using the word runtime for both. And I'm remembering that this problem came up in the slides once before, and I have to think about how to fix it. I would think maybe we think about T being the running time versus runtime. I don't know if that helps. It's not a big difference between running time versus runtime. But anyway, everybody get what we're doing here?
Sir,
Yep.
do you want to ask a question? So, like, like an algorithm, there is a fixed number of line, and doesn't matter what input you put, the line is not going to change, right?
Yes.
So,
Yes.
why do we have that statement there anyway? Why do we have the line function there? Like, I don't get it. Like the k is not going to change whatsoever, right?
Right. But you want to tell people that, right? You want to tell people, hey, k is not going to change with the input. You want to be able to say that.
Oh,
right?
so that is telling. Okay.
So here, the reason I say it is so that I can say it, right? Right here, in fact, what I need you to, when we go over to 2001 and we're talking about Turing machines, when I design the Turing machine, what things am I designing? How many states it has, right? What the transitions are, right? Those things are all defined at compile time when they're all fixed before you get the input. And you can't change them when you get the input. And I assure you, when you come over to 2001, you're going to know, you're going to get frustrated because for every input, there is a finite automata that will solve that problem for that input, right? I just have to give it enough states. But no, that's not the way the game works. You have to come up with my finite automata before you come up with the input. The number of states can't depend on the input. So you have to know, what does it mean? You can have as many states, you can have as many lines of code as you want. But you have to tell me it before you come up with the input. When I say they're constant, it means it doesn't depend on the input. All right? So I got really anal about people understanding this because I needed this was a finite state automata, and this was the number of states in that finite automata. But, that's more confusing because you don't know what a finite automata is, right? So instead, I'm talking about Java code and number of lines of code because you know what those are. And you know in your heart, you know that the number of lines of code doesn't depend on the input, right? So let's use that as an example to know what we're talking about, right? Would you agree that it is a little confusing? You can have, how many lines of code can you have? You can have as many lines of code as you want. You can have a billion lines of code, right? So is it constant? Well, it's constant with respect to the input. You can make your line of code, you can make your program as long as you want. But once you fix it, you can't change it when the input comes, right? And so that's another thing that this is saying is, it says there exists a k. I'm not telling you the range. You can have your k as big as you want. You can have as big k as you want. You can have as complicated as algorithm as you want. But each of these need to be finite. And then the input will come. And it will be bigger. And it will be scary. Winter is coming, right? This is like, you can prepare for winter. You can build up as much food as you want. But once winter comes, right, you better have enough food stored. So that's what we're saying here. Right? Does that make sense?
Doesn't also the number of lines of code depend on the algorithm too? Like if you have two different algorithms, it could be two different Ks.
Yeah, and here at compile time, you get to choose both the algorithm and the K. And as I said, it doesn't matter which order you put them. You could first say, hey, I want to write a code with K lines, and then you write the algorithm. Or you can say, I come up with the algorithm, and then I count the number of lines of code. It's all being done by the same guy in his room by himself. So he can do it in whatever order he wants. But yes, certainly a different algorithm would need a different K. But We're just saying there exists an algorithm, and there exists the k that goes with that algorithm. Right? Are people good? Hey, all of you guys on the first page here, at some point, I need to make sure I know all your names so that we can do class participation. Help me by remembering the names of all these people who talk, because I might not remember, but I certainly, their faces here I know, right? All right, so now everybody get this whole game about k versus the input, right? We're saying k it's a constant, it can be as big as you want, but it's a constant can be as big as you want. But why is it constant? It's constant because it doesn't depend on the input. Compared to the running time, right? The running time does depend on the input. And as you know, we don't want to just, right now we're not saying anything, which I guess in some ways we're saying t has to be finite, right? So there exists a t. In some ways I am saying something deep. The range on t are finite integers. So I'm saying the algorithm has to halt, right? Later, we'll talk about runtime, how the time depends on the input. All right.
Sorry, could you repeat that again? I didn't really like it. I was a bit confused. The last
All
one.
right. Good. So what am I saying about time? Here I'm just saying there exists a time, but it comes after the input, right? There is some running time, comes after the input. So the time does depend on the input. And then I said 2 points about that. The 1 point is that, well, I didn't tell you the relationship between input and time, and that later we will talk about the relationship between the input and the time. And 2, that still I am saying something here, right? This sentence about including time here does what it says is when I say there exists the time, I'm telling you that the time is finite, right? If this algorithm ran forever, then the running time would be infinity. And we're claiming it's not infinity because t here has to be finite.
Okay. Thank you.
Right?
So if
Everybody
t
kinda
is
get
in-
this?
So if t is infinite, that means it's not computable.
Yeah, well, it definitely means this algorithm didn't do it. Yeah, when I say computable, it means there's an algorithm that always stops. Algorithms that run forever aren't very useful.
Right, so
All right.
finite time.
Yeah. Everything, whenever I say exists, the domain here is always finite, right? There exists a finite algorithm, there exists a finite k, there exists a finite input, there exists a finite time.
So the t has to be finite for the algorithm to work?
Yeah, your algorithm has to stop.
Okay, thank you.
Right?
Is the statement still valid if t is 0?
Yeah. Maybe the algorithm just somehow magically knows the answer but doesn't run any time. That would be a little fast, but I'm not going to disqualify it. I don't want my time to be negative, but I can imagine some algorithm that's miracle does it in 0 time.
So if the input is not a finite number, does it mean it's like not computable?
Oh yeah. The domain here is finite. We're not talking about. I mean, there are computational problems that can have that can somehow we can model it as taking an infinite input. And then we would probably say the running time depends on the accuracy in which you want the algorithm to solve. But we're not doing that in this version of computer science.
Okay.
We're doing everything's finite.
But like in my head, I'm thinking of a scenario where you input an infinite number and your algorithm recognizes it and gives out an output saying you can't do that. Does that mean like that? Does that work as a program? Like because it's not computing
you can answer
anything.
that as well as I can. That seems like a philosophical question. How would you give an infinite input? We're not going to talk about infinite inputs here. All right. So let's talk about whether this sentence is true or not, right? So here was on my question. Is the sentence true or false? Explain. Decide. In fact, people in 2001, wasn't this assignment 1? I think this might have been assignment 1 for 2001.
Yeah,
Kind of.
I think it was.
Kind of. Yeah. Kind
Yeah,
of.
so this,
Yeah, I remember.
I don't know if it was assignment 1, but I think we've definitely done this before.
yeah, exactly.
But we have one more thing is the time has a limit there, like less than something.
Yeah, we're going to get into a limit here. Right now, I'm just warming up. All right. So, right, we want to know whether it's true or false. And if it's true, give me the strategy for the prover. It's false. Give me the strategy for the adversary. And what does it say about P, right? P is a free variable. So for some computational problems, this will be true. And for some, it will be false. And what we're going to say is it's true for problems that are computable, right? So if it's computable, then this sentence is true. And so the prover can win. And what do we mean by that? Well, how do we come up with the winning strategy? If it's computable, then the prover, he knows that it's computable, and he comes up with an algorithm that computes it. And then he counts the number of lines of code he has, and he calls that K, right? What does the adversary do? He says, oh, sad. He's very sad because he knows he's going to lose, right? He sadly knows that the prover's algorithm does, in fact, solve the problem, right? And he knows that it does, in fact, have K lines. So he has to come up with an input. So we could say, let I be an arbitrary input, or we could say, hey, he's a good sport, and he comes up with some input, right? And then it's an exist T. So what the prover does is he takes this input and he runs the algorithm on it, and he finds out how much running time is, and he tells you how much time is needed, right? And then we say, look at the prover wins. Why? Because it does solve the problem, it has the right number of lines of code, and we have the right running time, right? Everybody buy that? So now let's flip it around. If P is uncomputable, then this sentence is false. So let's see how the adversary can win this time, right? So first, the prover goes, and the prover is sad because he knows it's uncomputable. He knows there's no algorithm for it, right? But he does his best, right? We could say for all algorithms, let algorithm A be an arbitrary algorithm, let K be an arbitrary K, right? Somehow he comes up with some algorithm and some K, right? And then the adversary is chuckling. The adversary is very happy. He knows that P is uncomputable. So he knows that the algorithm A doesn't solve P on every input, right? Now, A might solve P on some inputs, right? So the adversary can't completely be lazy. The adversary has to find some input on which it doesn't solve the problem, right? So he finds some input in which the algorithm fails. And then the prover comes back, and the prover says how much time is needed for this algorithm on this input. And assuming the algorithm stops on this input, he could say some running time. And then, well, the prover, the adversary wins, right? Because the algorithm didn't give the right answer on that input. Everybody see how we're doing this? That's the game.